Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So today in this video lecture, we will understand the topic from Digital System Design KEC 302, and this particular code is specified in the syllabus of AKTU Lucknow, and the topic which we are going to take, which is little bit complex, and comparators are like the topics which are not very easy to understand. So we will discuss the comparators, to designing of these comparators using the various gates. We will understand the logic also. Now, what is a comparator? The comparator is a logic circuit which is comparing two binary numbers. Okay. So, the two binary numbers are being compared on the basis of their magnitudes. Let's say I have two numbers. One is A and another one is B. So, the comparator will perform the logic A minus B. If A is greater than B, one output G will be high. If A is less than B, L will be high. If A is equal to B, E will be. E is greater, it is less, and it is equal. There are three cases. So, this is the initial logic which we should understand. Now, which gate we will prefer for designing this logic? So, here for making a basic comparator circuit, the XNOR logic is being taken. Okay. Because why we are going to select this XNOR? Because if I see the XNOR circuit, let's say it is 0, 0, then output will be 1. So, this is the reason for selecting the XNOR logic. When the two bits are equal, then only the output is 1. So, what we are taking to design our comparator is XNOR gate. The comparator is XNOR gate. Okay. Because the output is 1 when the two input bits are same. Next. This is my circuit for 1-bit comparator. 1-bit comparator means A is of 1 bit, either 0 or 1. A is of B is of 1 bit, either 0 or 1. Right? So, there are three cases, L, E, G. Let us write the truth table for 1-bit comparator. Since it's a complex topic, so we need to clarify all these things. The possibility for A and B may be 0, 0, maybe 0, 1, 1, 0 and 1, 1. Right. So in this case, both bits are 1, equal will be high. Both bits are 1, equal will be high. A is less than B, then 1, this will be high. 1 is 1, 0, this will be, A is greater than B, this will be high. This is how the table goes, right? This is how the table goes. 0, 0, 0, 1, 1, 0 and 1, 1 are the four cases, and for which we have defined our truth table. Now let us make this table. There are 3 outputs, L, G and E. So E is X NOR of A and B, that we have already discussed in the last slide. So here A is equal to B, third case is A and B X NOR. Now what about A is less than B? A is less than B, for these two are covered. A is less than B for A bar B. A is greater than B for A B bar. So I have written A is greater than B, G is equal to A naught, A B bar. Actually here we are taking as A is equal to A naught and B is equal to B naught. And A is less than B, then A naught bar B naught. Okay. All my 4 cases, 2 cases are covered in this, 1 case in this and 1 case is in this. So this is the case for greater, this is less, and then this is for equal. Now I can design my logic using these 3 statements, and I can very easily design my 1-bit comparator circuit. So coming to this slide, here we have defined, this is A is equal to A naught and B is equal to B naught. A naught X NOR B naught is equal case, and B naught A naught bar is less case, and B naught bar A naught is greater case. Okay. So there are 3 cases which we need to define. Okay. Now coming to the 2-bit comparator circuit. 2-bit comparator circuit means here I am taking A as A naught A1, or you can take, in this we have taken AB, and B is equal to B1 B naught we have taken. Okay. For each AB, there are 4 cases of CD. Since there are 4 cases of AB, so we have 16 cases for complete A, B, C and D. So it is very clear that again we have 3 outputs, less than, equal to, greater than. 3 outputs we are having, less than, equal and greater. AB is less than CD, AB is greater than CD and AB is equal to CD. So all the three outputs we have written. Now we can write all the cases which are possible as inputs for the one number, first number, number 1, and for the number 2. For each AB, I have 4 combinations of CD, 0, 0, 0, 1, 1, 0, 1, 1. For 0, 1, we have again 0, 0, 1, 1, 0, like this. For 1, 0, I have again 0, 0, 0, 1, 1, 0, 1, 1. For 1, 1, I have again 0, 0, 0, 1, 1, 0 and 1, 1. So I have 16 possibilities of writing my table, less than, equal to and greater. So once my this side is clear, I can make the outputs to the right side. Okay. For 0, 0 and 0, 0, equal is high. For 0, 0 and 0, 1, less than is high, because my this number is first number, this is first number, n1. So I am performing n1 minus n2. 1, 0, this is again less, this is again less. 0, 1, this is high, this is equal, this is less, less. For this one, 1, 0, 1, 0, this is equal and this is greater than. Okay, so this will be high. For this one, only this is equal to, otherwise all are less. So I can write my truth table for 2-bit magnitude comparator. After writing this truth table, what should be the next step? I will make the K-map, because it is very clear that we have 3 outputs and we will make three K-maps to design 2-bit magnitude comparator circuit. So very easy, and in a very slow manner we can go for designing the circuits. So I have 3 K-maps for less than, equal to and greater than. So I will fill the entries for each output into my K-map. Since I have 4 variables A, B, C and D, so I have taken 4 cross 4 K-map A, B and C, D. So here we can solve the K-map as we do and we did in the last unit. The less than will come out to be this A bar B bar D plus A bar C plus B bar C D, and equal to will come out to be A of X naught C into B of X naught D. Greater than will come out to be B C bar D bar, A C bar and A B D bar. Okay, so there are 3 outputs and 3 K-maps we have designed. This is the complete logic. Using these expressions we can design. See here, this logic can be designed using this here, as we can say this is A naught is is first number, that is, just make the references, like we have taken number A as AB, and second is CD, and so in this case we can derive the greater than logic if AB is greater than CD, if AB is equal to CD, and if AB is less than CD. Number N1, number N2, number N1, number N2, number N1, and number N2. So by solving these 3 K-maps, we can design the logic for the 2-bit magnitude comparator circuit. Now coming to the 4-bit magnitude comparator. In the similar way, we can design the 4-bit magnitude comparator circuit. Let us see how we will design this 4-bit magnitude comparator. So here the logic for a 4-bit magnitude comparator circuit, let the two 4-bit numbers we are taking as A0, A1, A2, A3 and B0, B1, B2, B3. There are two numbers which we are taking, okay, and first if A3 is equal to 1 and B3 is equal to 0, then A is greater than B. Let us taking case by case. See, this is the case. I have these numbers. For each 4 number, I have 16 different combinations. Similarly, for the equal cases, as we did earlier, the NORs are concerned. The NORs are concerned. So what we can do is we can write the table and we can draw the references. So what are those references? Let us see one by one. The references which we are making by 4 logical expressions, let us discuss one by one each of them. This is pretty complex topic, so please understand carefully. The first case. If A3 is equal to 1, and B3 is equal to 0, definitely the number A is greater than B. Okay. So the first case is clear. The first statement is clear. If the highest MSB of A number is greater than the MSB of B number, second number, then first number is obviously greater than the second number. Now coming to the second case. If A3 and B3 coincide, let us suppose this is 1, this is also 1, and this is 0, and this is also 0. And if A2 is equal to 1 in this case and B2 is equal to 0, then A is greater than B. If A2 is equal to 1 and B2 is equal to 0, okay, this is 1 and this is 0, then A number is greater than B. If A3 and B3 are coinciding, means these two numbers are equal, then A2 is equal to 1 and B2 is equal to 0, then A is greater than B. Similarly, if A3, B3 and A2, B2 coincide, then if A1 is equal to 1 and B1 is equal to 0, then also A is greater than B. Similarly, if A3 B3 coincides, A2 B2 coincides and A1 B1 coincide, and if A0 is equal to 1 and B0 is equal to 1, then A is greater than B. So for A is greater than B, we have 4 cases. For A is greater than B, we have 4 cases and each are very clear. In which cases my first number is greater than the second number. Just comparing and taking the bits. Okay. So all these cases for A is greater than B. Similarly, we will write for the diagram. So here what we are doing is A is greater than B. All these cases we can draw. There are 4 inputs, 4 for these 4 numbers and 4 for A, B0, B1, B2, B3. Okay. So A3 is equal to 1 and B3 is equal to 0. A2 is equal to 1 and B2 is equal to 0. Okay. And similar way, this is what? This is the line for equal, and then we can connect it to the third gate. Okay. Similar way, if A0, B0, all the bit should be 1. These are all equal cases. And all inputs are 1, then only it should be 1 for equal case. For equal case, all should be 1. For less than, the second number logic will be same. What should be the second logic? That this is 1, this is 1, this is 1, this is 1, but these are all putting at 0. As we did in this one, and this is 0, 0, this is 0, like this. So all the 3 cases are drawn by logic, and we can design a 4-bit magnitude comparator circuit. So a 4-bit magnitude comparator can be designed. Once again we repeat, there are 2 numbers. First number is A3, A2, A1, A0, and second number is B3, B2, B1 and B0. Then let us discuss all the greater than cases. Greater than cases are when A3 is equal to 1 and B3 is equal to 0. When A3 and B3 are equal but A2 is equal to 1 and B2 is equal to 0. When A3 and B3 both are equal, A3, B3 and A2, B2 both are equal, then A1 is equal to 1 and this is 0. These 2 are 1, 1, these 2 are equal, these 2 are equal, these 2 are equal, and this is 1 and this is 0. Okay. So this is how the 4-bit magnitude comparator we have designed by logic. This is the greater cases. Similarly, for less cases we can discuss. If second number B is greater in which cases? Second number B is greater when B3, let us write this less than case, we will discuss again. This is clear because for equal cases we can design by using XNOR logic only. For less than cases, if okay, first case, okay, A3 bar B3. Second case, A3 is equal to B3 and A2 is equal to 0, B2 is equal to 1. Third case, A2 XNOR B2, B1 is equal to 1 and A1 is equal to 0. Fourth case, this along with this condition, so these are the cases when we can design the 4-bit magnitude comparator. Either this will happen, or this will happen, or this will happen, or this thing will happen. So in this way we can design our 4-bit magnitude comparator circuit. So we have studied the 1-bit comparator circuit, and then 2-bit comparator circuit, and then the 4-bit magnitude comparator circuit. By using case by case studies, we can design the comparators.